Hello, YouTube fan. Get ready for an amazing video experience. Welcome, curious minds, to our video that explores the ins and outs of estimation of covariance matrices. In statistics, sometimes the covariance matrix of a multivariate random variable is not known but has to be estimated. Estimation of covariance matrices then deals with the question of how to approximate the actual covariance matrix on the basis of a sample from the multivariate distribution. Simple cases, where observations are complete, can be dealt with by using the sample covariance matrix. The sample covariance matrix SCM is an unbiased and efficient estimator of the covariance matrix if the space of covariance matrices is viewed as an extrinsic convex cone in R. However, measured using the intrinsic geometry of positive definite matrices, the SCM is a biased and inefficient estimator. In addition, if the random variable has a normal distribution, the sample covariance matrix has a Wishart distribution, and a slightly differently scaled version of it is the maximum likelihood estimate. Cases involving missing data, heteroscedasticity, or autocorrelated residuals require deeper considerations. Another issue is the robustness to outliers, to which sample covariance matrices are highly sensitive. Statistical analyses of multivariate data often involve exploratory studies of the way in which the variables change in relation to one another, and this may be followed up by explicit statistical models involving the covariance matrix of the variables. Thus, the estimation of covariance matrices directly from observational data plays two roles: to provide initial estimates that can be used to study the interrelationships, to provide sample estimates that can be used for model checking. Estimates of covariance matrices are required at the initial stages of principal component analysis and factor analysis, and are also involved in versions of regression analysis that treat the dependent variables in a dataset jointly with the independent variable as the outcome of a random sample. In this segment, we'll be unraveling the complexities of estimation in a general context and exploring its multifaceted nature. Given a sample consisting of n independent observations xn of a p-dimensional random vector x column vector, an unbiased estimator of the covariance matrix, EIERT, is the sample covariance matrix. Marf equal I over n a sum I and xi over line xi over line marfmet, where xi is the ith observation of the p-dimensional random vector, and the vector I over line I over and sum I and xi is the sample mean. This is true regardless of the distribution of the random variable x, provided of course that the theoretical means and covariances exist. The reason for the factor n1 rather than n is essentially the same as the reason for the same factor appearing in unbiased estimates of sample variances and sample covariances, which relates to the fact that the mean is not known and is replaced by the sample mean. See Bessel's correction. In cases where the distribution of the random variable x is known to be within a certain family of distributions, other estimates may be derived on the basis of that assumption. A well-known instance is when the random variable x is normally distributed. In this case, the maximum likelihood estimator of the covariance matrix is slightly different from the unbiased estimate, and is given by marf n equal I over n sum I and xi over line marfmet. A derivation of this result is given below. Clearly, the difference between the unbiased estimator and the maximum likelihood estimator diminishes for large n. In the general case, the unbiased estimate of the covariance matrix provides an acceptable estimate when the data vectors in the observed data set are all complete, that is, they contain no missing elements. One approach to estimating the covariance matrix is to treat the estimation of each variance or pairwise covariance separately, and to use all the observations for which both variables have valid values. Assuming the missing data are missing at random, this results in an estimate for the covariance matrix which is unbiased. However, for many applications this estimate may not be acceptable because the estimated covariance matrix is not guaranteed to be positive semi-definite. This could lead to estimated correlations having absolute values which are greater than 1, and a non-invertible covariance matrix. When estimating the cross-covariance of a pair of signals that are wide-sense stationary, missing samples do not need be random, e.g., subsampling by an arbitrary factor is valid. With our curiosity piqued, let's embark on a dedicated exploration of maximum likelihood estimation for the multivariate normal distribution and its fascinating intricacies. A random vector X column vector has a multivariate normal distribution with a non-singular covariance matrix precisely if P is a positive definite matrix and the probability density function of X is factor pi frac per liter sigma frac I x buffed I over x mu mathmeter sigma x mu right, where is the expected value of X. The covariance matrix is the multidimensional analog of what in one dimension would be the variance, and a pi frac per liter sigma frac normalizes the density facts so that it integrates to 1. Suppose now that xn are independent and identically distributed samples from the distribution above. Based on the observed values xn of this sample, we wish to estimate. Let's now zoom in on first steps and uncover the hidden gems that lie within. The likelihood function is a mathcal mu sigma pi frac piprod I and deter sigma frac I x buff de frac x I mu mathmeter sigma x I mu right. It is fairly readily shown that the maximum likelihood estimate of the mean vector is the sample mean vector. I overliner fracs ergotsaxnen. See the section on estimation in the article on the normal distribution for details. The process here is similar. Since the estimate x does not depend on, we can just substitute it for in the likelihood function, getting a mathcal overliner sigma protoditor sigma frac x buffed I over a sum I and x I overliner mathmeter sigma x I overliner right. And then seek the value of that maximizes the likelihood of the data. In practice it is easier to work with log. Let's now turn our attention to the trace of a 1-1 matrix and examine its role within the larger context. Now we come to the first surprising step. Regard the scalar x I overliner mathmeter sigma x I overliner as the trace of a matrix. This makes it possible to use the identity trip equal to whenever A and B are matrices so shaped that both products exist. We get a beginnerliner mathcal overliner sigma protoditor sigma frac x buffed I over a sum I left x I overliner right mathmeter sigma left x I overliner right editor sigma frac x buffed I over a sum I operator one and left x I overliner right left x I overliner right mathmeter sigma right editor sigma frac x buffed I over operator one and left sum I left x I overliner right left x I overliner right mathmeter sigma right editor sigma frac x buffed I over operator one and left sigma right idaline, where sum I x I overliner mathmeter for pitums p. S is sometimes called the scatter matrix, and is positive definite if there exists a subset of the data consisting of p affinely independent observations, which we will assume. As we progress through this video, let's now turn our gaze towards using the spectral theorem. It follows from the spectral theorem of linear algebra that a positive definite symmetric matrix south has a unique positive definite symmetric square roots. We can again use the cyclic property of the trace to write editor sigma frac x buffed I over operator and left spracker sigma spracker right. Let B equals. Then the expression above becomes edit frac x buffed I over operator and right. The positive definite matrix B can be diagonalized, and then the problem of finding the value of B that maximizes edit frac x buffed I over operator and right. Since the trace of a square matrix equals the sum of eigenvalues trace and eigenvalues, the equation reduces to the problem of finding the eigenvalues. He that maximize lambda I frac x buffed frac lambda I right. This is just a calculus problem and we get I equal n for all I. Thus, assume Q is the matrix of eigenvectors, then B keep 1 ni P, i.e. n times the identity matrix. Prepare yourself for an eye-opening discussion on concluding steps in the upcoming portion of this video. Finally we get a sigma frac B frac left frac 1 ni pi frac frac south n. i.e. the sample covariance matrix. I show that n equal I over some I and x I over line x I over line approximate is the maximum likelihood estimator of the population covariance matrix. At this point we are using a capital X rather than a lowercase x because we are thinking of it as an estimator rather than as an estimate, i.e. as something random whose probability distribution we could profit by knowing. The random matrix south can be shown to have a Wishart distribution with n1 degrees of freedom. That is, some I and x I over line approximate w per sigma. Now, it's time to shift gears and explore alternative derivation. An alternative derivation of the maximum likelihood estimator can be performed via matrix calculus formula. See also differential of a determinant and differential of the inverse matrix. It also verifies the aforementioned fact about the maximum likelihood estimate of the mean. Rewrite the likelihood in the log form using the trace trick. On markal mu sigma e operatorn constanava on deter sigma I over operatorn and left. The differential of this log likelihood is don markal mu sigma equal frac no operatorn and left I over operatorn and left. It naturally breaks down into the part related to the estimation of the mean and to the part related to the estimation of the variance. The first order condition for maximum 0 is satisfied when the terms multiplying and are identically 0. Assuming the maximum likelihood estimate of is non-singular, the first order condition for the estimate of the mean vector is sum I and xi mu equal, which leads to the maximum likelihood estimator, a y hat bar x equal I over sum I and xi. This lets us simplify. Sum I and xi mu approximate sum I and xi bark sticks I bark stum approximate equal s, as defined above. Then the terms involving d and l can be combined as I over operatorn and left sigma right left right. The first order condition 0 will hold when the term in the square bracket is matrix valued 0. Pre-multiplying the latter by and dividing by n gives a wider sigma equal I over ns, which of course coincides with the canonical derivation given earlier. Dwyer points out that decomposition into two terms such as appears above is unnecessary and derives the estimator in two lines of working. Note that it may be not trivial to show that such derived estimator is the unique global maximizer for likelihood function. Now, let's redirect our focus towards intrinsic expectation and discover its significance in our narrative. Given a sample of n independent observations x n of a p-dimensional zero-mean Gaussian random variable x with covariance r, the maximum likelihood estimator of r is given by approximate equal I over sum I and x approximate. The parameter r belongs to the set of positive definite matrices, which is a Riemannian manifold, not a vector space, hence the usual vector space notions of expectation, that is approximate, and estimator bias must be generalized to manifolds to make sense of the problem of covariance matrix estimation. This can be done by defining the expectation of a manifold-valued estimator approximate with respect to the manifold-valued point r as left, where ix frac ix frac right ix frac left frac right are the exponential map and inverse exponential map, respectively. Exp and log denote the ordinary matrix exponential and matrix logarithm, and east is the ordinary expectation operator defined on a vector space, in this case the tangent space of the manifold. As we progress through this video, let's shift our attention towards bias of the sample covariance matrix and uncover its hidden depths. The intrinsic bias vector field of the SCM estimator approximate is defined to be left. The intrinsic estimator bias is then given by ix approximate. For complex Gaussian random variables, this bias vector field can be shown to equal approximate a beta approximate, where A beta panafrat palef pig n plus p epsilon n pepsilon epsilon ipsilon right, and is the digamma function. The intrinsic bias of the sample covariance matrix equals ix amarth patamarth ia beta panamartha, and the SCM is asymptotically unbiased as n. Similarly, the intrinsic inefficiency of the sample covariance matrix depends upon the Riemannian curvature of the space of positive definite matrices. In this chapter, we'll be shedding light on shrinkage estimation and its role in shaping our understanding. If the sample size n is small and the number of considered variables p is large, the above empirical estimators of covariance and correlation are very unstable. Specifically, it is possible to furnish estimators that improve considerably upon the maximum likelihood estimate in terms of mean squared error. Moreover, for NP the number of observations is less than the number of random variables. The empirical estimate of the covariance matrix becomes singular, that is, it cannot be inverted to compute the precision matrix. As an alternative, many methods have been suggested to improve the estimation of the covariance matrix. All of these approaches rely on the concept of shrinkage. This is implicit in Bayesian methods and in penalized maximum likelihood methods and explicit in the Stein-type shrinkage approach. A simple version of a shrinkage estimator of the covariance matrix is represented by the Leadoit-Wolff shrinkage estimator. One considers a convex combination of the empirical estimator with some suitable chosen target B, e.g., the diagonal matrix. Subsequently, the mixing parameter is selected to maximize the expected accuracy of the shrunken estimator. This can be done by cross-validation, or by using an analytic estimate of the shrinkage intensity. The resulting regularized estimator A1 can be shown to outperform the maximum likelihood estimator for small samples. For large samples, the shrinkage intensity will reduce to 0, hence in this case the shrinkage estimator will be identical to the empirical estimator. Apart from increased efficiency, the shrinkage estimate has the additional advantage that it is always positive definite and well conditioned. Various shrinkage targets have been proposed. 1. The identity matrix, scaled by the average sample variance. 2. The single index model. 3. The constant correlation model, where the sample variances are preserved, but all pairwise correlation coefficients are assumed to be equal to one another. 4. The two-parameter matrix, where all variances are identical, and all covariances are identical to one another although not identical to the variances. 5. The diagonal matrix containing sample variances on the diagonal and zeros everywhere else. 6. The identity matrix. The shrinkage estimator can be generalized to a multi-target shrinkage estimator that utilizes several targets simultaneously. Software for computing a covariance shrinkage estimator is available in our packages Quarka and ShrinkSubmit, in Python's scikit-learn library 1, and in MATLAB. I hope you learned something new today. Let me know what you found most interesting in the comments below.